We are Group 2, and this is our analysis and design improvements to can openers.
Can openers are used in both commercial and personal household settings. The can opener is placed on top of a metal food can and squeezed to cut through the top of the can with the blade. The crank is then turned as the gears spin around the can to cut, open, and remove the lid. The annual production volume is estimated at 50,000 units.
The primary customer for this product would be any typical household kitchen users. The average household would own one can opener. The secondary customer would be any household kitchen user that may require a can opener with adaptive features. This customer may be elderly or disabled and may not possess adequate hand strength to use a standard manual can opener. This slide shows the FAST diagram for this product. The FAST diagram identifies the important product functions and how they are realized by other subfunctions. This slide shows the function component mapping matrix, which illustrates which product functions are realized by which components.
The defined customer groups have different product demands. Derived from the function component mapping matrix, the module components that control these functions are defined as well as the platform parts common between each variant.
Here we can see the primary variant with standard length and size handles and a standard crank. Here we can see the adaptive variant. The handle length is twice as long to allow for more leverage while opening the can. It also features a mechanism that will hold the can opener shut while using to help reduce fatigue. The adaptive variant also features a new crank handle. This helps to increase leverage while turning the crank and can help eliminate problems for users with wrist issues.
Original and modified assembly sequences are shown on this slide, and the bottom sequence shows the components moved to later in the sequence to allow for delayed differentiation to accommodate both product variants in the most efficient way.
Here we can see the exploded views for before and after the redesign. The upper frame and handle clip were combined, the blade gear and spacer were combined, and the crank handle and twist wing pin were combined. More changes will be discussed further in the presentation.
The highest impact parts were found by analyzing the assembly's manual assembly time per part. The two highest assembly time parts are the handle grips and blade gears, but they each need to be a quantity of 2. The next top parts are the lower frame and the crank handle. The handle clip and twist wing pin were also selected for part consolidation. As seen in the quad chart, the lower frame is ideal for redesign, and the handle clip being the same material made it ideal for consolidation. As seen in the function component mapping matrix, the crank handle and twist wing pin share the same function of rotating the can.
In our redesign, we focused on part reduction, facilitating orientation, and providing locating features.
After the redesign was completed, efficiency increased from 42.1% to 46.97%. The cost per unit decreased from $5.90 to $5.76. And finally, the overall assembly time decreased from 64.13 seconds per part to 57.48 seconds per part.
The cutting blade, blade gear, spacer, and pin clip subassembly was selected as a candidate for high-speed automatic feeding, orienting, and insertion. These components were selected because they're all small and lightweight, they have some overlapping functions in the function component mapping matrix, and the spacer and pin clip are in the upper left quadrant of the quad chart, which suggests there's an opportunity for part consolidation. Design features were added to the pin clip, spacer, and blade gear to improve their total handling and insertion cost. For the pin clip, an upturned flange was added around the perimeter of the clip to prevent nesting and overlapping during feeding, supporting DFA Guideline 8. The blade gear and spacer were combined into one component, eliminating the spacer altogether, which supports the part consolidation DFA Guideline 1. Since consolidating the spacer and blade gear creates two unique gears that are very similar in size and shape, the combined gear and spacer is colored black using a chemical coloring process supporting DFA Guideline 9. The automated assembly time of the original design and modified design were calculated to quantify the improvement of the total handling and insertion cost. As is shown in the tables, the total assembly cost is reduced from $3.74 to $2.66, a 29% improvement. While the design modifications are generally positive for automated assembly and have no impact on product function, they have some drawbacks from a part manufacturing cost perspective. The added flange to the pin clip adds material to the component, which will incrementally increase part cost. Additionally, the added color to the combined blade gear and spacer will increase part costs. Lastly, combining the blade gear and the spacer creates two unique blade gears, which goes against the DFA 5 guideline of reducing part variety.
Looking at the function component mapping matrix, the lower frame and handle clip do not share any functives, so the redesign must capture the abilities of both components. Because of the product design and proximity to each other, the components can be combined into one single stamping. Key dimensions when combining these components is the location and size of the twist wing pinhole in reference to the pivot pinhole. In the drawing, we call out the pivot pinhole as a datum and govern the twist wing hole with a 5,000th true position callout, which will ensure the proper gear meshing when using the can opener. The hole is also sized accordingly for the twist wing pin to slide through it and tolerance at a plus or minus 5,000ths, which will ensure a good fit with the twist wing pin that will rotate properly.
Between conventional machining and sheet forming, we selected the latter.
In the original can opener design, where the lower frame and handle clip are separate parts, assuming 50,000 units are sold, the total manufacturing cost for both parts was calculated to be $2.21. After combining the lower frame and handle clip, as well as adding a bend for locating the twist wing pin, locating the can opener gear, as well as filling the missing thickness of the handle clip, the manufacturing cost decreased to $1.35 per part.
The analytical method provides a more conservative cost estimate when comparing to the Hub's website estimate.
The critical dimensions of the redesigned lower frame integrated with the handle clip remain unchanged and will allow for proper gear meshing and twist wing pin rotation. Looking again at the function component mapping matrix, the crank handle and twist wing pin share the functive rotate can, making them a strong candidate to be combined. The critical dimensions of this component are the length and diameter of the pin, so the stack-up of gears assembles properly and ensures proper gear meshing, and also must be long enough so the heat stake process constraining the gears in place. The print on this slide shows the pin length and diameter governed by a plus or minus 5,000ths for the length and plus 0 minus 10,000ths for the diameter to ensure proper assembly into the lower frame. These tolerances are achievable by the candidate process of injection molding.
The combined crank handle and twist wing pin will be manufactured from a thermoplastic material such as ABS. Of the candidate processes that are compatible with this material, only conventional machining and injection molding can support the shape, mass, section thickness, tolerance, surface roughness, and batch size required for this component. Our recommended manufacturing process is injection molding because the part geometry is relatively simple and can be easily molded. The part does not require very tight tolerances, and injection molding would yield lower part cost than machining at the annual volume of 50,000 units.
The crank handle and twist wing pin assembly cost per part was 82 cents before redesign. After the redesign, the new cost per part is 76 cents, which was an 8% reduction.
Using DfM Pro and the design principles learned throughout the semester, it was shown that the large mass in the center of the part created a sink during injection molding process. To eliminate this, 2 cavities were created to help alleviate the large wall thickness.
The post-DfM of the combined crank handle and twist wing pin maintains the key dimensions for part function. A section view is shown in this slide displaying the modified inside of the component redesigned by suggestions from DfM Pro. The following product service system will be introduced to improve the customer experience while reducing the negative impact on the environment and reduce customer cost. Partnering with our product distributors, we plan to offer a canned good recycling program that will give rebates for users recycling their used cans. Rebates and rewards will be tracked using a smartphone software interface provided after purchase of a can opener. Rebates can be used to purchase other handheld kitchen items that we provide and can be extended to more coupons and rewards provided by our distributing partners.
To summarize, after implementing the Design for Assembly guidelines, we were able to reduce the manual assembly time as well as reduce the automated assembly cost. After implementing the Design for Manufacturing guidelines, we were able to reduce the manufacturing costs for both the lower frame and crank handle assembly. To critique our modified design, both the lower and upper frames need to be modified to assist in alignment with the modified pins and gears. Furthermore, our design needs additional implementation of Design for Manufacturing guidelines for the remaining high-cost parts. If we were to start over again, we would start with the quad chart, as that guides what parts to start analyzing for cost and assembly times.